Welcome to this video on the classical Stokes theorem in three dimensions using differential forms. Now, Stokes theorem in R3 is a fundamental result in vector calculus that relates the circulation of a vector field along a closed curve to the flux of its curl across a surface bounded by the curve. This classical result can be naturally formulated using differential forms, which will make things a lot easier, as you'll see later on in the video. The difference between using the vector calculus approach and the differential forms one. Now, differential forms which generalize the concept of vector fields and integrals on manifolds. Okay, so it might help if I hide that. So a statement of classical Stokes theorem. So let S be a smooth oriented surface in R3, three-dimensional Euclidean space, with smooth boundary partial S, and let F be this vector field, be a smooth vector field. Then Stokes theorem states that the integral around a closed path, around the boundary there of f dot dr, is the surface integral of the curl of f, and that dotted with ds, which is the flux of the curl of f through the surface. So geometric and intuitive meaning. So the left-hand side, this, the closed integral around the boundary of f dot dr represents the circulation of f along the boundary curve, partial s. The right-hand side, this represents the flux of the curl of f through the surface. And Stokes' theorem states that the total circulation along the boundary is determined by the curl of the field over the enclosed surface. All right, so here's our surface S. Right, here's the boundary, partial S in the xy plane here. We have a vector field, smooth vector field, and some vector arrows are shown at different points on the surface there. You can see it's not all perpendicular to the surface there, so there is, as you would expect, there is a curl there, non-zero curl. Here's our boundary, so projected down onto the xy plane, and here's our boundary. Notice there's little vectors dr, little increments along the curve, okay, in the direction of the curve, going anti-clockwise, positive, okay, and these vectors are exaggerated in the diagram, but they're infinitesimally small vectors pointing along the curve. You have the vector field pointing out of the curve, out of the boundary here. All right, I'll adjust a few to show them. If we zoom in a little bit down here, we can see, and we pick this particular vector arrow here, F, we can see dr here makes an angle with F. That angle is theta. And this vector F can be decomposed into a vector that's parallel to dr, F parallel, and one that is perpendicular to dr. Right? Now, by definition, the vector F and the scalar product between the vector F and the vector dr is the norm of F times the norm of dr, or the magnitude of F times the magnitude of dr times cos theta. Now, when I say the part of F parallel to dr, I'm using just this notation here. So this is a vector which is parallel to dr at some given point. All right, so by definition then, using vector projection, the part F parallel is F dot dr on the magnitude dr times a unit vector in the direction of dr, which is dr on the magnitude of dr. So that's a unit vector here, which I'll call this symbol down here, dr hat. Then by definition, F dot dr is this, so I put that in there. That's magnitude F times magnitude dr times cos theta on the magnitude of dr in the direction of a unit vector dr. All right, they cancel, and we're left with the magnitude of F times cos theta times the unit vector in the direction of r dr. All right, so this is the component. And as we, at each point along this curve, as we go around along this boundary here, there will be a component at that point of the vector F parallel to dr, and it's these little components that we will sum up at each point along here. And they'll give us the integral around the boundary. Okay, now you can see where theta is equal to pi on 2 or 90 degrees, then cos of 90 degrees is 0, and so there'll be 0 contribution. If theta is less than pi on 2, less than 90 degrees, this will be positive. And if theta is greater than pi on 2 greater than 90 degrees, this will be negative. And so all these little bits of contribution that we sum up. All right, so the circulation integral. So imagine we walk around the loop, partial S, and at each point measure how much F is aligned with our direction. Remember, that's that component parallel to dr. Now, if F along the curve, if theta is less than pi on 2, it contributes positively. If F pushes against the curve, in other words, theta is greater than pi on 2, it contributes negatively. And if F is perpendicular, that's theta is pi on 2 or 90 degrees, it contributes nothing. So the integral of F dot dr around the boundary partial S is the total push of F around the loop. So you can think of the vector field F as a fluid flow, like wind or water current, and the integral of F dot dr around the boundary as the total flow along that loop. So how much the fluid pushes in the direction you're walking around the loop. So imagine you're walking anti-clockwise around the loop. What's the pressure of the wind or the water current on your back pushing you around the loop? That's, you can think of the circulation in that way. All right, now, at some points it's pushing you along the curve. At some points it's not pushing on you because it's perpendicular to you, to the direction of your travel. At other times it's pushing against you because the component F dot dr is pushing in the clockwise direction. All right, let's now look at the surface. So here's the curl of F. Here's at each point P, there's a vector because curl of F is a vector itself. This is ds, we'll talk about that later. All right, so curl of F is the curl of the vector field, and it's a vector indicating how much F swirls or rotates at a point. So each point of the surface feels some twisting influence from the surrounding field. Because remember, those vectors, they weren't all perpendicular to the surface. They're at different angles with the surface. And so locally, there'll be a sense of twisting. All right. All right, so we can compute how much that twist points through the surface using the dot product curl of F dot ds. Then we sum over all surface elements, so over all P, points P here, and that's the integral over the surface of the curl of F dotted with ds. And we sum up all of this, and this gives us the result is the net rotation, circulation per unit area pushing through the surface, a twisting effect pushing through the surface. How much twisting effect is there at each point P? It gives a global measure, when you sum it all up, of how much the field is rotating through the surface. What exactly is ds here? Okay, ds is the normal vector to the surface at each point times a small area element. So more precisely, the vector ds is the unit vector n times the surface scalar ds. So n is a unit normal vector, length 1. Ds, this ds here, is a small scalar area element. You'll see later in our example, it'll be dx dy on a flat patch in the xy plane. Now we integrate over the whole surface and pick up not just the direction normal, but also the amount of area at each patch. So this ds is not just a normal vector, but it's also got this amount, this little infinitesimally small dx dy amount. All right. So, but also the amount of area at each patch will integrate over the surface. So curl of F dot ds really means take the component of the curl of F, normal to the surface, multiply it by the small area ds. Okay, later on you'll see it's this. And then sum them over the surface, so, or integrate over the surface to sum up the total amount. All right, so differential forms version. To express this in terms of differential forms, we introduce the one form associated with F, so we use the flat operator, and we'll call this omega. So omega is the flat of the vector field F, and it's this object here. The exterior derivative d omega is a 2 form, is this. Now, this calculation, everything is all in previous videos. You look at the curl and divergence and so on of vectors in a previous video, and might be in one other video too. I've done all this as well elsewhere. It's not relevant to repeat it here. Here's just the result. D omega is this. I will just briefly, shortly state how it comes about, but just a brief reminder. You need to go back to those other videos to see the full calculation. So Stokes theorem in differential form states that the integral of d omega over the surface is the integral of omega over the boundary. This is an intrinsic coordinate independent formulation of the theorem. Okay, so what we're going to do next is go through some details. All right, so the exterior derivative and curl. The exterior derivative d in 3 dimensions corresponds to the curl of a vector field. That is, if omega is a 1 form associated with a vector field f, then d omega is interchangeable. It's the same as the curl of f. To see this explicitly, we express a vector field in differential form notation. So here we go. All right. Basis vectors, partial x, and so on. The corresponding 1 form, when flattening this, is, notice this, dx, dy, dz. All right. Notice this f1 and this f1 here, although the indices are placed in the upper and lower places, they are the same in Euclidean space. All right. Now computing, and that's what we're in, R3 Euclidean space. Now computing exterior derivative, d omega is df1 wedge dx plus df2 wedge dy plus df3 wedge dz. All right. Expanding using the definition of dfi, well, let's just look at df1. So df1 is partial f1 partial x dx, partial f1 partial y over partial y dy, plus partial f1 on partial over partial z dz, and similarly for df2 and df3, and then computing the wedge products, we obtain this. Okay, again, as I said, it's been done in previous videos, so it's not the purpose here to go through it or the place to do it here. I'm just quoting the result. This shows that the components d omega correspond exactly to the components of the curl of f. That's these in the parentheses here. Okay, so outline Stokes theorem in R3. So step 1 is parameterize the surface. So let S be parameterized by some position vector R of UV in Euclidean space, which is components x of uv, y of uv, z of uv, where uv range over some domain R2. All right? So we're parameterizing it in 2 dimensions in terms of 2 uv variables. Now the tangent vectors to this, which will help us find a normal vector shortly, but tangent vectors are RU is partial R on partial U, and RV is partial R on partial V. They'll give us the tangent vectors at each and every point on the surface here. All right, and then the induced surface element then is this vector ds, which is RU cross RV. This is the cross product, so this gives us a vector perpendicular to both RU and RV, and then times the surface scalar element du dv. All right, remember this will be normal to the surface. Now, using the exterior derivative, we compute the integral d omega over s over the surface is the integral of this, okay, in Euclidean vector calculus. These 2 things that give you the same result. Now we apply the fundamental theorem of calculus. By applying the fundamental theorem of calculus for line integrals, the integral d omega over s is equal to the integral of omega over the boundary partial s. That's Stokes theorem. Example. So that's an example of Stokes theorem on the hemisphere. I'm just going to go through and show you, outline the vector calculus approach and show you how the differential forms one is simpler. All right, so consider the upper hemisphere of the unit sphere, this one. X squared plus y squared plus z squared is 1, as we saw earlier. We just want the upper part, as we saw in the diagrams near the beginning of the video. And here's our vector field f. In the x component is minus y, the y component is x, and the z component is 0. So step 1, compute d omega. Well, the corresponding 1 form of this is going to be minus y dx plus x dy. Remember here, because this could be expressed as partial over partial x, partial over partial y, partial over partial z, okay, and then the flattening operator, I think you get the idea, gives you this object here. We take the exterior derivative, so d omega is minus dy wedge dx plus dx wedge dy. Now the anti-symmetry implies that this can be reversed and becomes a negative, so we get dx wedge dy plus dx wedge dy, so it's 2 lots of dx wedge dy. They compute the surface integral. Suppose the surface S is given by Z is f of xy, some function of xy. where x, y are coordinates on some domain D contained in R2. Okay. So then a parameterization of S, R of xy, becomes our position vector R of xy, reducing from 3 dimensions to 2 dimensions, pulling it back from 3 dimensions to 2 dimensions. We get xy, f of xy belongs to R3. This vector belongs to R3 as an element of R3. Okay, but expressed in terms of the variables x and y only. All right, so the tangent vectors to the surface are partial r and partial x. Is, well, if we just go back here, partial r, partial x, well, that becomes 1, that becomes 0, and this becomes the partial f with respect to partial x. So that looks like this. Partial r and partial x is 1, 0, f of x. Partial r, partial y is 0, 1, fy. That's where f of x is partial f on partial x and fy is partial f on partial y. The infinitesimal area element ds, which is normal to the surface, is given by the cross product of these two tangent vectors. So ds becomes partial r, partial x by crossed with partial r and partial y, and then the scalar areal element dx dy. So let's compute the cross product of this. I just thought I'd put this in just for completion, just make it easier for you to follow. But if you, whatever method you've got, expanding out using Cramer's rule or adding the extra 2 columns here, that's common. You'll get this, whatever your method is. It gives you this object here, this vector. I as a unit vector in the I direction, x direction. J as a unit vector in the y direction, k as a unit vector in the z direction. And so partial r and partial x crossed with partial r, partial y is this object here, and hence ds is this vector dx dy. The magnitude of ds gives the area form, so this gives you that, and hence the scalar area 2 form on S is this object here, dx wedge dy. All right. Now, so that's converting there to a 2 form, scalar area 2 form. Now, ds can be written as ds is n ds, where n is the unit vector, where the unit normal vector is in general, n is ds on the magnitude of ds, or the norm of ds, and that's just this object here, as you'd expect. I'll just put that in for completeness. All right, now returning now to the matter in hand, there is an easier way to approach this by noticing that d of omega, exterior derivative of omega, is this object here, as we saw earlier. Here's our vector field. Putting those in, well, F3 is 0, so that goes in there. F2 is x, so that goes in there. You notice that component will go to 0. Similarly, if we do the same here, F1 is minus y, put that in there, that'll go to 0. F3 is 0, so that component goes to 0 as well. The only surviving component is this one. Partial x on partial x, well, that's 1, and partial negative y on partial y is minus 1. So we get 1 minus minus 1, which is 2, and dx wedge dy, that survives. Okay, so 2 dx wedge dy. Now, since d omega is 2 dx wedge dy, and that's equal to this object here, all right, because remember the integral over the surface, remember Stokes Theorem, the integral of the surface over the surface S of this is equal to the vector calculus approach with the integral over the surface of this. So that means d omega and this are equal. So we have that the curl of f then becomes 0, 0, 2. You can read that off. All right, think about it. 0, 0, 2. So we get 2 in the k direction, and ds becomes dx dy in the k direction, and then the absolute, or the magnitude of this vector ds is simply the area scalar dx dy. All right. So you can see k dot k is 1. Okay, so 2k dotted with dx dy k is just going to give you 2 dx dy. All right, so that means n is this, that on that, which is just k as you'd expect. We must have as a 2 form ds is dx wedge dy. which we integrate over the disk x squared plus y squared equal less than 1 here. We have pulled back d omega to the unit disk in the xy plane. Remember, we pulled back from this from 3 dimensions to 2. Then the integral over the surface of d omega is the integral over the surface of 2x wedge dy, which this is the area of the unit disk, so it's 2 times the area of the unit disk, and the area of a unit disk, that's pi r squared. R is 1, so it's just pi, and with the factor 2 here means we have 2 pi. Next step, compute the boundary. The boundary is x squared plus y squared is 1 with parameterization x is cos t, well, natural parameterization, x is cos t, y equals sine t, and t is between 0 and 2 pi. When we do that, so over closed boundary partial s of the 1 form this. Okay, we'll substitute in minus sine t. The differential of that is sine t dt. Okay, dx is sine t dt. Remember, x is cos t, and the differential is minus, so minus sine t dt. And then here, x is cos t, and then dy is cos t dt. Then notice that we're going to have the 2 negatives cancel here. We're going to end up with sine squared t plus, sorry, that, my terrible fault there. That should be cos squared t here, cos squared t dt. I missed that in the check. Terrible. That should be cos squared t there. Sorry, everyone. And together that gives us 1, and then the integral of that from 0 to 2 pi is just 2 pi. And this verifies that the integral partial s of f dot dr, that's the part around the boundary of f dot dr, is equal to the integral of the curl of f dot ds, which is the flux of the curl over the surface s. And it just shows that the integral of omega around the boundary is the integral over the surface of d omega. So Stokes theorem in R3 naturally follows from the properties of differential forms. The exterior derivative provides a coordinate-free way to express curl, making the theorem an elegant generalization to higher dimensions and curved manifolds, which we shall be looking at next. So in the next video, we'll look at Stokes theorem on curved manifolds. We're going to show that the integral of the manifold M of d omega is the integral of omega around the boundary of the manifold. That's what I'm going to be getting at in the next video. I look forward to seeing you in the next video. I hope you found this useful. If you do, or if you want to, please push the like button and subscribe if you will. I'd greatly appreciate that. I look forward to seeing you all in the next video. Thank you very much for watching. Take care and enjoy your day. All right, until next time, bye.